For this month's MYSO STEM session, we'll be hearing from Science Olympiad alumnus Dr. Sarah Lipsey of Ball Aerospace. She will share her academic and career journey with us today.
I was in the 7th grade when I was introduced to Science Olympiad. My middle school team did not have a team that had 7th graders in it, so I was on kind of a junior team in practice, and I got to watch the senior team do their business and compete, and it was really fun to watch. And so by the time I was in the 8th grade, I was on the formal team, and I can't tell you how exciting that was, and sort of how much pride I got in being on the team. My middle school science teacher, Mr. Hounsel, is who introduced me to Science Olympiad. He was one of the coaches at our school. And so he recognized in me, something and introduced me to the team, and off I went. And he and his wife, Mrs. Hounsel, were very important role models in my early career in the Science Olympiad. So as I said, I was on this junior team to begin with, and one of the events that I was trained for was called Whether or Not. I think that's still in play these days. And so what we did there was learn about various weather phenomena. We read science textbooks so that during the event at Science Olympiad, we took a test. And I remember being very anxious about taking a test, even though, of course, that's what you do all through school. But man, those were the easiest tests I ever took because I was so well prepared and knew what was going to be on the tests. When it got hard was when we went to nationals. And instead of just a multiple guess test that we had to take, we were literally given weather maps. So a map of all of the winds and all of the temperatures. And the test was to draw the weather front across the state and to figure out exactly where it needed to be. And then not just that, but to predict the weather in a city on either side of the front that was predetermined. And I remember that being so challenging, but so fun because it brought all the things that I had learned together into one event. The other events I really liked were anything where you got to build something. When you build the bridge and get to break it, building windmills, building model airplanes, sort of anything that you then get to go test. I really, really like building things. So Science Olympiad runs in my family. When I started, my mom would often be one of the parents that came along with us. As my siblings, I have a younger sister and a younger brother. They both got involved and were on the teams in Delaware. And these days, my dad is actually the coordinator for the state of Delaware for Science Olympiad. So the tradition continues even though it's been a long time since I competed. So my advice, if those of you out there are interested in science, technology, get involved. Science Olympiad is a great opportunity not just to hone your skills, but to work with teams and get to figure out really challenging, hard problems together. I mentioned building bridges, right? That's a really hard challenge. You have to figure out how you can build something that's not going to break easily. And it's always good to have teammates that you can bounce ideas off of and work through challenges together. I'll say too, reach out into your community. There's always lots of resources, places to go, science museums, observatories, all these kinds of things are great resources to help you learn what you're interested in, because if you do what you love, you will do it really well. I went to college at the University of Colorado at Boulder, and I studied physics. And it's a little bit of a funny story because most of my life I thought I was going to be a chemist. And that's because that's really all I knew. Growing up in Delaware, you'll know I went to HB DuPont Middle School and AI DuPont High School, and DuPont is a very large company in Delaware. And a lot of my friends' parents worked for DuPont, and they were all chemists and various kinds of scientists. And so I was going to be a chemist. But my family let me come out to the University of Colorado between my junior and senior year in high school, and I did a summer program. Randomly got placed in an astronomy program, And my instructor, who's a professor at the university, said to me, there is no reason you should study chemistry. You should study physics. It's the basis for everything. And off I went. So now I'm a physicist. I have a bachelor's degree in physics from CU Boulder, and then I went on and got a PhD in astrophysics from UCLA, the University of California at Los Angeles. And that is a fantastic program. You get a master's degree in a few years and then a PhD in a few more years after that, where you get to really hone your skills in doing independent research, working with teams but also by yourself, and becoming an expert in your little corner of the universe. And I have to say, it's really hard work to do that, but it's really, really empowering. For my PhD work, I did nighttime astronomy. I'm an observational theorist. So my projects were involving getting small snippets of observations, usually at the Keck observatories in Hawaii, or the very large array of radio telescopes. Also little bits and pieces of data from other observatories, almost always ground-based in my case, and then building models around what we were looking at. Most of the targets I looked at were evolved massive stars. These are the kinds of stars that will someday go supernova, but have not yet. And so we were really studying them in detail to learn when they go supernova, how might we predict that their supernova will look, and really understanding the predecessor, the precursor star before it goes supernova. So I helped develop that whole body of work for what those stars look like, so that when they do pop in a supernova explosion, we'll have a lot of great data about them. And so as you'll see from this picture, I continued to be involved in Science Olympiad. This is a picture of me sitting with Mrs. Jill Hounsell. She was one of my mentors in Science Olympiad when I was in school, but now at this point I'm in college and I've come home for spring break, and I'm helping her grade, actually in this case, astronomy questionnaires, exams from the Science Olympiad in Delaware. So when I was in graduate school, as I said, I was studying astrophysics. And one of the things I will definitely recommend to anyone is explore all your options. And so here's some pictures of me at the Mount Wilson Observatory. This is the Solar Physics Observatory just outside Los Angeles. We use this data, I actually used this data for my master's thesis, which was in helioseismology. So using sound waves moving through the sun to detect what's going on inside the sun, where things are moving around. And so this is the Mount Wilson Solar Observatory that we used. And the other picture is me in my hard hat with some of my other astronomer friends. We're actually up in one of the very large array dishes. So this is an array of 20-some radio dishes. They're each ginormous. And you can see there's a lot of us up there. You have to wear a hard hat because there's radio receivers that are up above us that could, I suppose, potentially fall on us. But it was a really cool experience to go out and get to see how that all really works. I was finishing my PhD career, had some conversations with my thesis advisor about what I was going to do next. And sort of the traditional path when you get a PhD is you go do a postdoctoral research appointment somewhere. And I was starting to realize at the time that that was really not for me. I kind of wanted to get out of the research realm and do more enabling of science rather than the research itself. And so we had lots of conversations and had the opportunity to apply to Ball Aerospace, which is in Colorado. And so I got to come back after Ball offered me a job. I was hired to Ball as a systems engineer. That's typically what we do with most of our scientists, PhDs of all types. And so I've worked at Ball for a long time now as a systems engineer. I've also functioned as a program manager. And these days I'm the acting director for Civil Space New Business. That means I run the team that writes all the proposals for all the cool missions that we chase. One of the very non-standard things, but coolest things I get to do is attend rocket launches. Very often, maybe a couple times a year, we'll launch something into space. These pictures here are of the IXB rocket. So this is out in Florida at the Kennedy Space Center. And we launched IXB, off it went. It's in low Earth orbit now, and it is operating fantastically 1 year into its 2-year mission. At Ball Aerospace, we do not just astrophysics missions like the IXB mission that I talked about, but also missions across observations of all things, including our own planet, which is a very important planet, and it is a member of our solar system. And as an astronomer, I'll say we use the Earth as an example of a habitable planet. And so as we start to look with James Webb Space Telescope or future observatories into where planets in our universe might be habitable, we use our Earth as an example. And so to do that, we really need to understand our own planet very well. And a lot of instruments and missions that Ball has worked on focus very heavily on the Earth. And so here's an example. This is the JPSS satellite, which has a little instrument on the tail called OMPS, the Ozone Mapping and Profiler Suite. The Ozone Mapping and Profiler Suite was built here at Ball, as was the spacecraft for JPSS-1, which is now called NOAA-20, now that it's operational. And these instruments and the mission itself are very important low Earth observation systems for monitoring weather patterns and understanding the impacts of change in our climate and also our more frequent daily, kind of weekly weather monitoring. The JPSS-1 mission, which is now called NOAA-20, is a very important mission for the US and globally. It has 5 instruments that help us monitor weather and climate. Not just pretty pictures of hurricanes, but also really important things like the Antarctic ozone hole and how the ozone hole is actually improving now that the world community has come together and banned the chemical substances that diminish the Antarctic ozone hole. The other instruments on there you'll know from some of your daily weather forecasts. So these are things that measure water and temperature in the atmosphere so that we can predict your weather better every day. One of the culminating things that we get to do, of course, when we finish a mission is launch it. And in total, I've worked 4 launches in my time at Ball Aerospace. I also have gotten to witness many of the launches, just watching NASA TV. Highly encourage anyone, go watch a launch, right? It's just so motivating. And if you ever get to see one in person, be prepared. It shakes your body to the core when that sound wave comes past, but it is exhilarating. Launching things into space is one of the most magical things that we do. And having the team next to you that worked on that mission with you is also just magical, right? All of the energy and all of the excitement just comes to a culmination. And I will say that working on those teams is one of the best parts of getting to work at Ball and getting to work in this field. One of the highlights of my career at working at Ball, but also hearkening back all the way to my 7th and 8th grade and then high school experiences with Science Olympiad, is working with teams. It is one of the most beneficial things that you can do in your career. Today, I work with teams all the time, multiple, probably dozens of different teams a day. And I will say that at Ball, a lot of my best friends have come from teams that I have worked on, in pursuits, on programs, in launch campaigns. You get to know those people really, really well. And then you spend your time after work, maybe on the weekends, going on hut trips, going on ski trips, doing hiking adventures, just having everyone to come over to your house and have a beer on the porch. Really great friendships are formed through these things. But at the same time, working on those teams at work is just really rewarding, and getting to know everyone and all of their family structures and values has been really, really fun. Highly encourage you, join lots of teams, even if they are stretch goals for you. They may not be right in your wheelhouse, but go out and join. And Science Olympiad is a great opportunity to form those relationships. One of the most exciting things that happened in our field in the last year was the launch of the James Webb Space Telescope, or Webb. This is the most exciting thing because it is a massive telescope that is much bigger than the Hubble Space Telescope and can see in a different wavelength range, so it can see out to the beginning of the universe. And this is exciting because why would you want to see the beginning of the universe? Well, we want to learn how it started, right? So how does this happen? At Ball, we built the shiny gold segments that you see in the primary mirror. There are 18 segments. They're each about 1.5 meters across. And here's an example of a miniature version of that. Gold on one side, but here's where the magic happens. On the back, there's this hexapod actuator that actually pushes and pulls on the different chunks of the mirror, so that once the mirror was launched, our scientists and engineers could align the telescope very, very precisely when it made its way all the way out to the L2 spot. Very complex time to get out there, the observatory unfolded, and all of our mirrors were aligned. Now we have the most precise telescope out there ever, and it's enormous. The gold mirrors and the cold temperatures of the mirror allow us to see into the infrared. So this is way past where our bodies emit into the thermal infrared, and it's where the early universe started to send off early photons. So we're starting to see first stars, first galaxies, starting to see structure in the universe. In this picture, you see an artist rendition of Webb, and in the background, you can see down here in the corner the sun and the Earth, and there's a little moon. And this is because the Webb telescope is way out at L2. So this is a Lagrange 2-point for Sun-Earth, and it's a sort of an equal gravity spot where it doesn't take a lot of energy to hang out there. This spot rotates in the same fashion as the Earth around the sun, so it goes around once a year. And it means that it's far enough away that there's no way we're going to take a picture. So the best we can do is this artist rendition. But you can see how far away it is. We cannot also reach it with astronauts right now to go replace things, which was why it was so important to have the mirror be really well aligned once we use our actuators, because we can't really go fix it. So the most exciting thing, though, from the telescope, of course, the technology and getting it launched, but are the images that we're starting to see and the data coming back from the observatory. So you'll see all these pictures that will flash by, but they're gorgeous pictures of star-forming regions, or galaxies interacting, or finding out that planetary nebula are actually dual star systems in the case of this Southern Ring Nebula. Or learning about how galaxies are evolving in the case of this Cartwheel Galaxy, where you see these crazy star formation regions happening. All of these images are coming back because scientists across the world are writing proposals asking to have Webb stare at various spots in the sky so that they can take those observations. And I would encourage you to get involved in teams who are maybe proposing these observations so that you too can help make some of these discoveries. We're going to continue to see amazing imagery, spectra from Webb. Not just from Webb, but there's lots of new telescopes for astronomers to play with in the works. And again, I want to emphasize that science is not just astronomy, although it's the best one. But we can do, photons are photons. So photons from Mars are equivalently observable and measurable and understood. And you can measure photons from the Earth and learn about Earth and how the Earth is changing and how the Earth works, how our system works. These are all really, really important things, and we can all help each other by forming teams and doing these. When I'm not at work, I have a lot of hobbies that I love to do. Of course, I'm an avid reader. I live in Colorado, so of course I know how to ski and snowboard. I'm a big swimmer, and I like to spend a lot of time with my family. So my family does almost all of those things with me. My little man is learning how to ski, and he loves to hike, mostly for the snacks. But we also spend a lot of time exercising and playing in the yard. We have a wonderful garden, and it's just really fun to play as a family and learn each other's personalities. So I want to encourage you all, in closing, to be an explorer, to be a space explorer, be an Earth explorer, whatever you need to be. And I want to say, too, that not everyone is going to be a scientist, and that's fine. It takes everyone to enable these big missions that we undertake. We need business analysts, we need structural analysts, we need leaders of all kinds to help us make the right decisions and figure out how to best solve these really tough problems. And of course, we need scientists to ask the questions so that we know what to build and provide data for to answer your questions. So everyone is going to play a part in this. I hope to see you at Ball someday, but even if you don't come work at Ball and come say hello to me, I encourage you to be a good citizen and learn all you can so you can ask really important questions and make very important decisions.